So every type of volume we've looked at has had a circular cross-section, but obviously not every solid has a circular cross-section. So we want to have a look at ones that don't have circles. We can still use the same idea by chopping up the shape. So let's have a look at a shape where we know a formula for it, and that is our rectangular pyramid. I want to slice it and come up with slices so that each slice still is a similar shape. So I guess there's a couple of ways I could do it. I could do it horizontally, and then it's a rectangular pyramid, isn't it? So then every slice would be a rectangle as we go down. I suppose I could do it vertically. What would we get? We get trapeziums as we slice. I mean, the middle trapezium would actually end up being a triangle, but, you know, I think I'll do it the easy way and go with the rectangles. So if I slice it that way, now I've got to give it some dimensions. The fact that there's no number plane there doesn't really matter, because all the number plane really is doing is giving us a relationship between y and x or what have you. And that's all we really need to. We know we want it in terms of its thickness. So I need to come up with a relationship. I've called the sides of the rectangle, my slice here, x and y. So I needed a third pronumeral, logical to pick z. So I said, the thickness is z. So I want to get an expression for x in terms of z, and I want to get an expression for y in terms of z. So there's my rectangle. Thickness is z. At this stage, I know the height's y, and the length is x. How on earth am I going to do that? Well, at this stage, I've got x times y, but that doesn't help me really. Let's just look at x in terms of z. So I turn that three-dimensional picture into a two-dimensional picture. So in other words, let's imagine if I just do a cross-section. So all I'm looking at is the x dimensions and the z dimensions. So the z dimensions is the height of the pyramid. Because, let's put the slice in so you can see what I'm talking about. So there's the slice. So all I'm seeing is that edge of the slice, which we know has width x. And if I was to chop there, I'd see a triangle. And the base of that triangle, when I look at that bit, would be B. And I know that height is h. Now, the relationship between the two, it's going to be a linear relationship, because there it is right there. That's a straight line. I could, if I want to, put axes on there, but effectively I'm saying, hey, what's the equation of this line right here? So I could do it that way. And there's another way I could do it using geometry. So I'll do that first. I could use similar triangles. Some people like to do it this way. I go, all right, I've got similar triangles. I certainly know that the big triangle, which has got height h, base, will it be half a b on that one. And then if I have a look at the top triangle, the height would be h minus whatever the z value is. And then the base would be a half x. So z, we're defining, I guess, from the bottom going up, how high it is. So whatever the z value is at that point, the height of the triangle would be h minus that. They're similar triangles, so I can set up my ratio, rearrange it, and I get x in terms of z. Remember, b and h are constants. So I could do it that way. Personally, I prefer to use coordinate geometry. And this is how I would do it on this one. I'd say, all right, I'm going to get coordinates, z and x, and I'm basically trying to get the relationship between the two. And what some people find hard to get their head around is, I've put x where we normally see y. But it doesn't matter, they're just pronumerals. You could put x in first and z second, it doesn't really matter, because you're just trying to find a relationship between x and z. The reason I put x second is because that's what we want to make the subject in the formula. And if you think about number plane graphs, we normally make y the subject, so the second pronumeral the subject. That's the only reason I put it second. Could have had it the other way around, doesn't matter. Okay. Now at the top of this shape, I'm going to define the x value here. Well, I can't just pick it, because remember, x is the width of the slice. So I know at the top, the width of that slice is 0. There is no width to it. We've come to a point. And we know the height of the triangle, that's what z's representing. The height of the triangle is h. The other place I have a definite knowledge of is the base. At the base, the height is 0 because we haven't gone up yet, and the width of the slice would be b. So I now have 2 points. Well, if I've got 2 points and I know it's a straight line, I can come up with the equation of a line just using our point slope formula. So my slope would be, well, normally we'd say y2 minus y1 thing. I suppose I'm going to think of it as the second coordinate. So b minus 0 over 0 minus h, rise over run. And the slope is b over h. This is where you've got to be really careful, because normally we go y minus equals slope x minus, but in this case it'll be x minus the value. I've chosen to use the top point. So x minus 0 minus b on h is z minus h. And there we go, we get the same formula. It's a matter of choice, really, how you go about it. I say a lot of people do use similar triangles to do that sort of thing. Personally, I go with coordinate geometry. That's my preferred method. Okay, now I'm not going to do the y one because it'll be exactly the same if you think about it. It's just you're turning the shape around. The only difference is the width of the slice now would be y, because we're looking at the other side, and the base, instead of being b, is a. Everything else is exactly the same. So I know that, okay, well, that equation would turn out to be y equals a h minus z over h. So the x has replaced the y, and the a has replaced the b. Well, if you wanted to prove it, you could, but trust me, it does come out to be exactly the same thing. Now it just becomes exactly like all the other questions. There's my area function. I have it in terms of z. Tidy that up a bit. ab h minus z squared on h squared, which means the element of the volume would be that times the thickness. Set up my sum. Now z, remember, is the height, so we're going from the base where it's 0 up to the top where it's h. And so that's what we're integrating. I've pulled all the constants out that I can, so AB over h squared's out the front. So all I'm really integrating is h minus z all squared, which is actually a nice little integral. Add 1 to the power over the power, but in this case it's minus z, so we'll end up with minus 3 on the bottom. Substitute in h, substitute in 0, and there's the formula we're used to seeing. 1/3 of ABH. Base times width times height. Let's have a look at this little interesting one. This is another type of one where they told us we have a circular base, and every cross section is going to be a square perpendicular to that base. Now, this time I am going to put, because they've given me the equation of the base, I've put the number plane in there. And so it's a circle, so let's imagine our number plane is sitting on the table, if you like. So that's why I've put it at a funny angle. We're sort of trying to draw a three-dimensional shape here. Each cross section is a square perpendicular to the base. So something like that. There's a square perpendicular to the base. There's another one, and 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 another one. I don't know if I did another one. Starting to get a feel for what this shape or solid would actually look like. So what we got is it would end up being like a cylinder that's been shaped. I kind of think of it like a bike helmet. Yeah, it's got that funny sort of arching shape on a bike helmet. I attempted to join those. It didn't quite work out the way I was planning there, but there you go, that gets that sort of bike helmet idea of trying to join all those points. Not exactly perfect, but all I've got to do is apply the same idea. I want to add up all of those slices. So each slice I know is a square. What are its dimensions? Well, the thickness, the way I've drawn it, is in terms of x. So I want everything in terms of x. But the base of my square would be twice the y value. But it's a square. So the height would also be twice the y value. So I know the overall area is 4y squared. But I would like that in terms of x. Well, we've got a lovely formula up there that links x and y. Very easy to make y the subject of that one. So it's just 4 outside of 4 minus x squared. from this point on, exactly the same as we did with all the others. Okay, my element of volume, I'd multiply that by delta x. So I'm going to sum, and I'm going from -2 through to 2. In this case, I do have symmetry. It would be exactly the same volume on the left-hand side there as it would be the right-hand side. So I could go twice 0 to 2, and the integral 4 minus x squared. Subbing, there's our answer. So these parallel cross-section ones, I guess the more involved part is not so much the integration. It's the coming up with a formula for the slice. Sometimes it's nice, like this one was nice because they told me it was a square, so I just had to work out the base. The one before that I had to work out both sides and how am I going to get a relationship. Here's one from an HSC, and I think the text was meant to be over there, but something's happened anyway. So what do we got? There's a quarter of a cylinder radius r. The base of the solid, it's just this little wedge shape we're going to find the volume of. The base of the wedge is an isosceles triangle, so ABC. The length of BC is A. Oh, okay, so that's the base of that triangle. Midpoint they've labelled X. Cross sections, so all of these cross sections are rectangles. So we know our slices are going to be rectangles. And there was no hints or anything, it just simply said, find the volume. Find the volume. Okay. Well, there's my slice. Well, what can I do? I've just called the thickness Z, so I'll use that as the pronumeral for the thickness. So I've got to get the dimensions in terms of Z. Okay, I'll call the base little x, I'll call the height y, and you can see I've also added that on the diagram as well so I can see what I'm looking for. So x is that bit there, y down the side. Alright, yeah, well, okay, yeah, area x times y. I guess that was the easy bit. Let's first of all look at y. Now, to get y, just looking at that part of the slice, I've got to look down through the quarter cylinder. So what would I see? I'd see a quarter of a circle. There's the slice. We're trying to get an expression for the height of that slice in terms of z. So I've given the slice coordinates zy, because I want to end up with y in terms of z. Now, if I define up the top there to have a z value of 0, so I'm going to start my slicing over here at the a's. So here it's 0, and up the top, I know that height is the radius of the cylinder. And over when I get to x, it'll be the other way around. Z will have got to r, and the height is now 0. But it's not going to be a linear relationship, because look at this curve. It's going to end up being a circle, or a semicircle, or something like that, the relationship. So it's not linear, which means I can't use similar figures. And I guess that's why I prefer using the coordinate geometry idea, because I can apply that idea to every problem. Linear shapes, fantastic. I do similar figures, and a lot of them are linear shapes, but occasionally you get ones like this. Well, really, when you think about it, we know the equation of the semicircle. A is now like the origin, because that would be 0, 0. We're saying, what's the equation of a circle, or a semicircle in this case? Radius r, well, r squared minus z squared. I've got it, beautiful. There's my relationship between y and z. What about x? So now, when I look at it, I'm seeing that isosceles triangle. So I'm actually looking down on the shape. So what I'm seeing is the base. And the base was that isosceles triangle. And there's the slice. So I'm looking down on it. There's the slice. So again, this time I'll give it coordinates zx. Now, at the top, I can't change what z is. So I chose z to be 0 over here at the top, so it's still 0 over there. Can't just swap it. And at the top, I've made x equal to 0 as well. At the top, it's got to be 0, because remember, x is representing the width of the slice. And at the top of the triangle, it has no width. And then we'll go down to the base, and at the base I know the width, so the x value is A, but also I know from my diagram over here that the z value is r at that point when we get to the end. There's my two coordinates. This time it is a nice linear function. It's a nice straight line between the two. So let's find the equation of that line. Slope ends up being a over r. Put it into our point slope formula. And there it is, x equals az over r. Alright, we've done the hard bit. Remember we said area was simply x times y. Multiply those two things together. Get our element of volume. Now the z, we're going from 0 to r. 0 to r. There's our integral. Ooh, oh hang on. The z out the front, that's good, because the derivative of z squared is 2z, so I've got a function times derivative situation there. See, I could rewrite that as minus 2z, which is the derivative of minus z squared, and obviously I can't just magically put the minus 2 there, so now I've divided by minus 2 out the front as well. So it's power of a half, add 1 to the power of 3 on 2, 2/3, sub in, and we get our answer. Now of course what was difficult about that question, they gave you no hints at all how to approach it. You had to come up with all of those ideas yourself. So you can see that, gosh, if you can't come up with the dimensions of the rectangle, where do you go? Where do you go? I mean, I suppose you could fudge it a bit and come up with some weird formula for x and so at least you had something to play with. I mean, I can't guarantee that it'll get you any marks, but who knows what the marking scheme's going to say. They might say, oh well, all right, your functions were wrong, but at least we can see you knew. As long as your integral didn't turn out to be a lot easier than that, I don't know. I can't guarantee that, but I think maybe that's what I'd do in that situation if I wasn't sure. By the way, that was the average that year, 1.01 out of 4. That's across the whole state. That's not just our school. That's the whole state, 1.01 out of 4. Well, let's see how we go with some of those ones. As I say, they can be the more fun ones, because as you can see, you've got to somehow create the formula for the slice. I think the ones where they tell you the equation of the base are probably easier, because at least you've straight away got a link between y and x or something like that. The one like that last one there, they tend to be the more trickier of the type.